Welcome to this presentation of our paper on automatic detection and classification of head movements in face-to-face conversations. My name is Patrizia Paggio. This is joint work with Manesh Aguirrezabal, Barhongeyan and Costanza Navarrete. Here you see what we look like. I will be doing the presentation together with Manesh. Head movements have a number of important functions in communication. Therefore, conversational systems must be able to deal with them both in analysis and generation. Our goal here is to identify different types of head movement automatically from conversational video data. Head movement detection has been attempted previously on the basis of track data. It is more difficult to detect head movements only using the raw video data by means of computer vision. Several attempts have been made at combining visual features with text or speech features. Work has been done on different movement derivatives and also on how to use acoustic features to detect, for instance, agreement signals, all of which is relevant to us here. In our method, we train speaker-independent models to recognize head movements in video data based on different combinations of visual movement features, acoustic features from the speech signal, and word features derived from the transcriptions. We further develop an approach presented in 2018. Here we're working on a larger dataset that involves 12 speakers, and we try to distinguish different movement types. Our corpus is a collection of Danish first encounter dialogues involving 12 speakers. Each dialogue is of about 5 minutes for a total length of approximately 1 hour. The two speakers are standing in front of each other, as you see here. They are recorded using 3 cameras and 2 microphones, and this is the view that is used in this study to predict head movement. We have a number of different notational layers, 2 of which are relevant here. First of all, the manual orthographic transcription, from which we derive the word features. And secondly, the manual annotation of 8 different head movement types, which constitutes our gold standard. The kappa scores we obtain for head movement annotations are reasonably good, so between 0.7 for identification and 0.8 for classification. Here are some statistics. You can see here that about 2/3 of the frames in the video do not contain head movements, whereas about 1/3 of them does. And here we are distinguishing between 3 different classes. So these are the ones that we want to be able to detect: nods, shakes, and a class we call other, in which we have merged the other types. This is the average number of frames per speaker, and the standard deviation here shows us there's considerable variation.
Let's move on now to the visual features. In previous works, we used OpenCV to detect bounding boxes around the face, and the center of the bounding box generally coincided with the nose. In these experiments, we used OpenPose. OpenPose detects up to 25 body parts in 2 dimensions, and we only use the X and Y coordinates of the nose. OpenPose's nose detection proved to be more reliable than OpenCV, and this could be because while OpenCV misses frames in which the face is partly occluded, OpenPose detects virtually all faces, even those of dolls. Here you can see a representation of different features that can be captured by OpenPose. At this moment, we only use, as we just said, we only use the nose, but as you can see, we have plenty of other features that we could use to extend our work. So we have plenty of things to experiment in the future. For each frame in a movie, we compute velocity, acceleration, and jerk, both in the X and Y directions, and both for the person standing to the left and the person standing to the right. And the reason for this is that a sequence of frames with a high jerk value may correspond to the stroke of the movement. To compute velocity, acceleration, and jerk, we used nose position data from sliding windows centered around the current frame. So we used the surrounding frames of the current frames. So these sliding windows have different numbers of frames for velocity, acceleration, and jerk, 9, 11, and 13 respectively. And velocity, acceleration, and jerk are computed by linear, quadratic, and cubic regression over the respective data windows. In terms of acoustic features, we used the mean F0 and intensity values, which were sampled with 25 frames from the speech signal using Pratt. And the reasoning for this was that head movements are likely to co-occur with prosodic stress, and stress in Danish is expressed, among other things, through F0 and intensity. Therefore, changes in speech or peaks of intensity might be associated with head movement strokes. And we also used word features, which is just a binary feature saying whether the gesture is speaking or not. And the reason for this is that an analysis of data from two of the speakers in our dataset showed that voiced sequences have a higher probability of co-occurring with head movements than unvoiced ones. Okay, so we obtained all the manual annotations of head movements and also the time-stamped transcriptions of the words from Anvil, which is the software that we use for annotation of the videos. And we got all that information for each frame in each movie between the start and the end of each dialogue. We also extracted the acoustic features from Pratt, and then the computed velocity, acceleration, and jerk data were aligned with the Anvil and Pratt data. And then the resulting datasets, we had 12 TSV files, which at the end, they constituted 24 training sets, because each of those 12 files had information to 2 people. So then we ended up having 24 different training sets. Okay, we validated our models using a leave one speaker out cross validation, where for each speaker, we saved one speaker for testing and we trained the model with the remaining speakers. So in this way, we created speaker independent or subject independent models. And the task that the classifiers were trained for, well, first of all, we trained classifiers for predicting presence or absence of movement, thus binary classification, and we also trained classifiers to predict the kind of movement, which was multi-class classification, in which the models should distinguish between nods, shakes, other kind of movements, and no movement. So here you can see like a summary of the features that we use, the feature sets that we use. So as we mentioned, we used in some first experiments, we trained models using only visual features. Then we also trained models using visual features, but also with acoustic features. And then we trained models with visual features, acoustic features, and word information. We used 2 different baselines. One of them was just a most frequent strategy, which predicted always that there was no movement, because that's the most frequent class. And also we used a logistic regression with only velocity features as a baseline. And then the classifiers that we trained, they were logistic regression, linear supervector machine, and a multi-layer perceptron as a neural network. So let's see the results. First of all, if we see the results for the binary classification experiment, one of the things that we can say is that all models perform better than the most frequent baseline. Apart from that, the multi-layer perceptron or the neural network outperforms all other classifiers irrespective of the feature combinations. And we can also say that the MLP or multi-layer perceptron is the one that varies the least across the speakers. We cannot see that in this table, but there is in the article, there is a figure where we can see the variation across speakers. And the MLP is the one that varies the least. Apart from this, if we take a look at the multi-class classification results, we could see that this task is more difficult and therefore results are lower. In this case also, all models perform better than the most frequent baseline. In this case also, the multi-layer perceptron or MLP outperforms other models, and the recall is rather low while precision is slightly better. Now to conclude with the results, let's take a look at the error matrices of one of our models, and as you can see, all types of movement were confused with no movement, which is it's normal because no movement is the most frequent class. But also one of the interesting facts that we can see is that nods and shakes were the most precise kinds of movement that were predicted. And this could be because they're rather different, these kind of movements.
It is not easy to compare our results with the state of the art because different studies work with different data sets and report results in different ways. The work that is perhaps the most similar to ours is the one in Fried et al. 2016, where head movements are detected in Swedish TV broadcast data. The others also rely on movement derivatives in a similar way to what we do. However, they predict for each word and not for each frame whether it is accompanied by a movement or not. The best results, 0.9 accuracy and 0.61 F1 score, are quite similar to ours. However, in a way our task is more difficult because we are detecting head movements from full body size and the quality of our videos and audio is far from optimal. So it is fair to say that our results are at least state of the art. If we compare with our previous work, where we performed head movement detection in data from only 2 speakers. In that work we obtained 0.75 accuracy with a multi-layer perceptron trained with visual and acoustic features, so the method was similar. And in this work, the accuracy of the best classifier goes down a little bit. However, it is obtained on a much larger data set, which shows the robustness of the approach. Finally, we want to raise an issue that has to do with the way in which the golden standard was annotated. So the human annotators annotated not individual frames, but whole movement segments, whereas the classifiers predict the value for each frame. So is it at all reasonable to compare the results of these two processes? Well, in order to do so, we tried to approximate the work of the annotators in a way by looking at the number and duration of uninterrupted movement frame sequences and comparing those with the gold standard. And as you see, there are about half as many annotated movement sequences in the gold standard as there are in the predicted movements. However, the duration of the annotated ones is much longer than the one in the predicted ones. So the classifier detects many more but shorter movement sequences. This difference is illustrated in this density graph that shows the distributions of the durations in the annotated versus predicted movements. And you see that in the predicted ones there are in the predicted ones there are many more very short movements. We then tried to ask ourselves why that might be the case. And the hypothesis is that long head movements in the annotation may contain a hold or a repeated gesture. You see here that the user made a repeated nod, which the classifier would probably recognize as a sequence of different movement frame sequences. So, in conclusion, head movements can be detected in unseen speaker data by an MLP classifier trained with multimodal data, and the results achieved perform at state-of-the-art level. However, when the same method is applied to the classification of 4 different types of head movement in the same data, their performance decreases. We have a number of ideas for how to take this work further. First of all, we want to look more at the comparison of the annotated and the predicted movements. We want to experiment with adding more features from on-purpose using different computer vision techniques, investigating the use of more acoustic and word features, or maybe applying them in a more selective way. And finally, we'd like to experiment with sequential models such as recurrent neural networks that have been shown to be quite efficient for this kind of task. Thank you very much, and we'd like to acknowledge the support of the GEM Research Network on gesture and head movements in language.